So this is one of the negative of the Hamiltonian. It doesn't matter, but this is related to the Hamiltonian of the system. So now, what about in thermodynamics? I have S as a function of UVN, correct? Or since I'm talking about, we'll be talking about free energies, we'll start with U as a function of SVN. I want to replace the volume, correct? If I want to replace the volume, then I have the prescription that is given to me that I need to define a new function which is y minus m times dy dx. Here it's a function of a single variable. I can generalize this. Therefore, I will define a function which is u minus v del u del v and, well, and s also. This is allowed, correct? What is this function? But this is u and del u del v is PV, and this I know is the enthalpy H. So I have defined a new thermodynamic potential where essentially is I have defined a new thermodynamic potential where I replace the volume by its conjugate force P, and clearly you can see that H is a function of S, P and N. So that means for an adiabatic isobaric process, the enthalpy remains a constant quantity because there is no variation. So if you look out dH is going to be del H del S ds plus del H del P dP plus del H del N dN. And since I have said that it's an adiabatic process, it's an isobaric process, this is 0, this is 0, and this is always 0 because I always take n to be fixed. Therefore, dH is 0, and that essentially means that there is no change in the enthalpy. I can replace S. So let me write down S del U del S Vn n constant. This is U minus ds because I know that this derivative is equivalent to t. And this quantity is known as Helmholtz free energy. Since I have replaced S and I have brought in T, the Helmholtz free energy is a function of TVN, and clearly this means that dF is del F del T dt plus del F del V dV plus del F del N dN. Isothermal process without mechanical work implies F is constant. So isothermal means dt 0, mechanical work is 0. Well, this is always taken to be 0 because there is a fixed, it's a fixed system with a fixed, it's not an open system. So here, therefore, F remains constant. So you use the Helmholtz free energy whenever you have an isothermal process without any mechanical work. There is no volume expansion or so, and in which case the free energy remains the same. I have now, before I do the next step, one thing I want to emphasize that you see, if you might ask that if I want to calculate, I want to express F as a function of SVN, or I want to look at u as a function of tvn. If you work it out this way, then you will see that not all thermodynamic properties are known. So this is like specifying c as a function of x that we had discussed earlier. Now coming back to this, I have u as a function of svn. I have been replacing one variable, one generalized coordinate. I want to replace two. Let's replace s and v. That means I want to construct something which is del u del s vnn constant minus v del u del v snn constant. This I can easily do u minus ts plus pv, right? And in thermodynamics, this is what is called the Gibbs free energy. So now you must be utterly confused that why have I introduced another Gibbs free energy? You have to look at the Gibbs free energy very carefully. T, V and N. Now I have replaced V with P. dg is del g del t dt plus del g del p dp. I am holding n constant, but never mind. So del g del n dn, right? In the presence of a constant constant mechanical force, isothermal process in the presence of a constant mechanical force Gibbs free energy remains constant. So isothermal process, constant mechanical force, this term is we always ignore because it's a closed system. Therefore, there is no particle exchange that is allowed. So therefore, the Gibbs free energy remains constant. So there are two free energies. One is F as a function of TVN. The other one is a function of TPN. They have different uses for different realizations. In this case, you have a thermostat and volume fixed. And in this case, you have a thermostat as well as a barostat, right? So in that case, the Gibbs free energy becomes the dominant, remains constant throughout the process. So now we have seen how to use Legendre transformation, and we start off with this and slowly can eliminate the generalized coordinates. So if we eliminate entropy, then we define this as not an equal to, but we define it as u minus Ts, which is my Helmholtz free energy function, which is tvn. And since it's a function of tvn, I can write down this as del f del t vnn constant dt plus del f del v tnn constant dv plus del f del n tnv constant dn. If you look at the left hand side, df is also identically du minus tds minus sdt. And if you recall your first law, tds is equal to du plus pdv minus mu dn. So this means du minus tds is, let's is minus P dV plus mu dN. So you immediately see, if you compare, that del F del T Vn constant is minus S. Del F del V Tnn constant is minus P. Del F del N Tnv constant is the chemical potential mu. So these three quantities can actually help you to determine the entropy, the pressure, and the chemical potentials. These relations, sorry. So once you know the Helmholtz free energy is given to you, you can calculate this entropy from this relation. And if you know the entropy, please note that you can calculate U minus Ts is equal to F, which implies the internal energy is equal to F plus Ts. I can manipulate this expression, and let's just do it very quickly. It's a very simple exercise. So this is del F del T. Let's be very careful here, plus T del F del T, volume and N constant, right? So this I can write down del T of F times T. Am I right? So if I do that, then the first term is F and the second term is T del F del T, volume and N constant. So volume and particle number constant is implied over here. But one can just calculate the internal energy as a function of U. And once you know the internal energy as a function of U, you know the entropy, you can eliminate the forces to reconstruct back U as a function of SVN. So these are always the trick that you play. So you know F, from this you calculate S, from this you calculate U. And then you also know P and mu, the generalized forces that is given to you, and F is always going to be a function of what? Is going to be a function of T, V and N. So you see, from these relations you can eliminate T and you can reconstruct back the fundamental relations, U as a function of SVN or S as a function of UVN. We will do it as an exercise at the later stage. Then we had U minus PV, U plus PV, which was the enthalpy, and we said that this is a function of S, P and N. So if this is a function of S, P, N, then we said that this is going to be del H del S, P and N are held constant ds, del H del P, S and N are held constant dP, plus del H del N, S and P are held constant dN. If I look at the right hand side, dH is also identical to du plus pdV plus vdP. du plus pdV is what? Is tds plus mu dN. So that I have tds plus vdP plus mu dN, right? And therefore immediately the derivatives again follow. Del H del S, P and N are constant, is equal to T. Del H del P, S and N are constant, is equal to V, and del H del N, S and P are held constant, is equal to the chemical potential mu. One can again reconstruct back the U from these relations. What about the third term of interest, which is G? G we constructed by replacing both the entropy as well as the volume, so that this was G which was a function of T, P and N. And if I do it, du, dg is del G del T dt. I'm not going to write what is being held constant because now I know that you have a grasp of what should be held constant. dp plus del G del N dN. Right. So then dg is also du minus dds minus sdt plus bdv plus vdp. So dds is du plus bdv minus mu dn. So this quantity becomes mu dn minus together with this one du plus bdv. This becomes minus sdt plus vdp. So that del G del T N and P held constant is the entropy, del G del P N and T held constant is the volume, and del G del N T and P are held constant is the chemical potential. These are the derivatives which are of interest over here. But remember, we did the Euler relation for the energy. What does that Euler relation give us? That U was a function of SVN, therefore we had del U del S times S plus del U del V times volume plus del U del N times N, right? This was the Euler relation. So we knew that U is equal to Ts, and then this is going to be del U del V is going to be plus PV minus mu N. So it follows that U minus Ts minus PV is minus mu N. There is a problem with the sign over here. This has to be minus. So let's rub this. This has to be minus. So U minus Ts, and this has to be plus. U minus Ts plus PV is plus mu N. If that is the case, then I clearly see that G of T, P, N, and this follows all the way from this relation that we have defined, is equal to mu times N. Correct? So that del G del N is equal to mu. It is consistent with this definition. But what is also consistent is that if you see over here, both of these are your intensive variable, and there is no homogeneity property associated with this. The only thing that is associated with this is N. This is my only extensive variable, and therefore I must have G of T P lambda N must be equal to lambda times G, and if I want to apply the Euler relation, I am going to get the same thing as this, that N times if I want to apply the Euler relation, then this is going to be del G del N times N, and this is equal to mu times N, which is the relation that I have over here. So everything becomes consistent with this. Interestingly, you should know that once I have this, then G by N is small g, which is a function of T and P, because N has been taken out over here because you have put lambda is equal to 1 by N, and that essentially is the chemical potential. So the Gibbs free energy density is the chemical potential. Right? So that means it's interesting. That means, how do you define the Gibbs chemical potential? Well, it's the amount of energy, the change in the free energy, or amount of energy that I have to, well, the change in the Gibbs free energy per particle. That essentially defines my chemical potential mu.